Right, let's get straight into it. Zero fluff today. In this explainer, we are tackling a seriously high-yield and honestly fascinating topic for Cambridge AS and A-Level Physics 9702, thermal conductivity and vibrations. We're going to build an incredibly focused understanding of the underlying science and, more importantly, exactly what examiners demand from you, so we can finally stop leaving those easy marks on the table.
Listen to this exam answer on solid lattice dynamics. Quote, vibrations move heat, which is why microchips overheat. I mean, it sounds completely logical, right? But believe it or not, writing that exact sentence just lost a student 3 crucial marks. It's painful. It's the kind of subtle omission that acts like a slow leak during an exam, quietly dragging down your grade boundary. And the worst part? It leaves you wondering where on earth you went wrong when you felt so confident about the physics.
Okay, let's dive into this. We've got our flawed answer, which, let's be honest, is really just a scattered collection of basic ideas. And contrasting that, we have this massive blank space where a perfect, top-band answer should be sitting. You see, ordinary revision fails because it stops at simply memorizing a term like vibrations. It completely forgets to link that term to the incredible physical reality of what's actually happening down at the atomic level. By the end of this explainer, we are going to completely fill in that blank space with the exact, precise scientific wording your examiners are desperately searching for.
Section 1. The 4-step exam formula.
So here is the master formula. It's an absolute game changer. To secure those top marks on extended answers and truly prove you grasp the physics, examiners want to see these 4 specific stages, and they want them in exact order. First up, the definition of the concept. Second, the microscopic mechanism at play, like what are the atoms actually doing. Third, the macroscopic consequence, which is what we can physically measure in the lab. And fourth, the real-world application. If you can string these 4 elements together, you construct a literally flawless scientific argument.
Keep this in mind. A disciplined paragraph that connects cause and effect usually scores far more strongly than a scattered collection of random facts. Now, in just a minute, I'm going to reveal the exact examiner clue that changes everything about how you approach these exam papers. But actually, scratch that. Before we get there, you absolutely must understand the physical, microscopic picture, because without that scientific foundation, this framework doesn't mean a thing.
Section 2. Inside the crystal lattice.
I want you to build a visual memory palace with me right now. Just imagine zooming in, right past the shiny surface of a metal, shrinking down, 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 until you are standing right in the middle of a vibrating grid of atoms. Down here is where we find our core definition. Thermal conductivity and vibrations is defined as the interpretation of a solid's macroscopic behavior based on internal atomic or carrier-level mechanisms within elementary lattice dynamics. It's such an awe-inspiring concept when you think about it. What a material does on the outside, like, say, glowing red hot, is entirely 100% dictated by the microscopic, invisible dance of atoms and charge carriers on the inside.
And this brilliantly illustrates the massive leap in vocabulary you need to make. Everyday language just says, heat moves through the solid structure. Sure, fine for the street. But in A-level physics, your technical vocabulary must sound like this. Energy transport via internal atomic lattice vibrations and carrier mechanisms. You really have to upgrade your phrasing so you don't accidentally confuse related macroscopic concepts. We aren't just talking about generic heat anymore. We are talking about the physical transport of energy through a highly structured atomic grid.
Now, to make sure you never just freeze up under exam pressure, rely on the number 4. These are your 4 memory trigger prompts for this whole topic. 1. What is the concept? 2. What changes inside the solid's atomic structure? 3. What is observed outside the solid? And 4. Where does it matter in technology? Seriously, practice answering those 4 prompts out loud from memory, and I promise you your understanding will be rock solid.
Section 3. The real-world physics trial.
Let's put the physics on the witness stand for a second. We are demanding hard evidence and scientific reasoning to explain real-world phenomena. Think about how we connect the macroscopic evidence directly to the microscopic scientific reasoning. Like, why do microchips overheat? Well, it's because carrier-level energy transport, that's the movement of free electrons, hits its physical limits. Or, how do thermal barrier coatings protect massive jet engines? They do it by utilizing phonon scattering. A phonon is basically a quantized packet of vibrational energy, and scattering disrupts its flow, acting as this invisible shield against extreme heat. And acoustic crystals? They rely entirely on engineering that exact vibrational behavior.
Now, what's really interesting about this is that these practical applications aren't just fun trivia.
They are the absolutely critical fourth step in our exam formula. Overheating chips, thermal barrier coatings, acoustic crystals, and extreme temperature sensors. In fact, if it weren't for these specific mechanisms acting to dissipate energy, your smartphone processor would literally melt its own casing in seconds. No joke. Knowing these applications proves to the examiner that you understand why vibrational behavior actually matters in the real, physical universe.
Section 4. Top Band Examiner Correction.
Let's do a quick pause and predict interactive challenge. Listen to this typical application statement. If a student simply writes, "The device heats up," can you spot the missing microscopic link there? Like, what exact physical mechanism are they completely failing to mention? Take a second to predict what the examiner is actually searching for.
Well, if you didn't connect it to lattice dynamics or phonons, you just fell right into a trap. Here are the most common traps where students bleed marks on the 9702 paper. Trap 1. Stating the correct term, like vibration, without explaining what is physically happening to those energy packets. Trap 2. Giving an application entirely without the microscopic reasoning to back it up. And Trap 3. Just dropping fancy technical vocabulary onto the page without showing any clear cause and effect. It happens all the time.
So, the crucial point is understanding the difference between a flawed answer and a fully healed top band response. Listen to the flawed version again. Chips overheat because of vibrations. Now listen to the top band version. Chips overheat because internal atomic level vibrations and carrier interactions limit the rate of thermal energy transport. I mean, just look at that beautiful cause and effect. We took the macro application, linked it straight to the atomic mechanism, the carriers and vibrations, and used incredibly precise technical wording. That is how you win.
So, to guarantee that disciplined, high-scoring paragraph every single time you sit down to write, let's do a rapid-fire recap of your mental checklist. Number 1, definition. Number 2, mechanism. Number 3, consequence. Number 4, application. Write your exam answers following this exact sequence, and you will consistently demonstrate top-tier understanding to the examiner.
Let's move to and see how this builds, because here we face a pretty stark reality. Knowing the theoretical phrasing is incredibly powerful, yes, but it's still only half the battle. What about the linked practical and data analysis skills? Because without mastering how to actually analyze the data that proves these thermal properties exist in the lab, those highest grade boundaries, they are still locked away from you.
Think of it this way. Your post-surgery rehab isn't finished yet. We have successfully fixed your theoretical paragraph structure today, but to truly conquer Cambridge 9702 physics, you have to apply all of this to experimental variables and practical investigation design. How exactly do you design the practical experiment to plot this thermal data? Master that, and you don't just understand how the universe handles heat, you unlock the A-star to prove it. So until next time, keep questioning the physics behind the phenomena.